Pretty good one from you, Angela. See, it's kind of like when my wife tells jokes, she's not hilarious all the time like me. But sometimes she drops like the random just bombs on you. It's like really funny because she said it. All right. So we were, if I remember correctly, getting ready to implement our CPU or simulate our CPU.
Yes.
All right. Okay. So in our driver, right now we're just creating one PCB, but we started working on the process scheduler last time. Process scheduler is going to maintain three different, one list and two queues. So we're going to have a list of all the jobs that exist in the system. Then we're going to have the list of things, the queue of things that are currently ready for the CPU. And then we're going to have the device queue, things getting ready to enter the device. When we start a process, so this is going to be the process scheduler being told, start the Microsoft Word process, for example, even though in our case, we're not telling it which process to create, we're just having it randomly generate a process for us, add it to the jobs list, and then add it to the end of the line for the CPU. All right. Then we started writing the CPU data structure. CPU data structure is going to keep track of the current PCB that's running in the CPU, the current program counter. It will have a line of code that's the current instruction it's working on that it's going to have to decode, and then a collection of the registers. So in our mimicked world here, these are the actual CPU registers, these guys. A PCB holds a copy of what the last state of the registers were when it was last on the CPU, so it can reload them next time. All right, so think of our PCB as a data structure that tells us about a process, where the CPU is our programming simulation of an actual piece of hardware that has real hardware registers in it and that stuff. Make sense? So this is a machine. So it's our virtual CPU. All right. So when we first install our CPU, it has no process currently running on it. So that's why we have cur PCB is null. Now we have the ability to context switch in. So that means a process will be loading into the CPU using the PCB data structure to load everything in. So we'll set the CPU's current program counter to whatever that PCB's program counter is. We'll read in the temp registers from the PCB, then load them into the actual hardware registers in the CPU. Okay? And then we're ready. For our small example, we're ready to go. At that point, a PCB has made its way from the ready queue into the processor, into the CPU. But we also need to support context switch out. So that is the PCB that's going to be leaving the CPU only to either get back in line for the processor or to go wait for I/O. So we'll have public void context switch out. Okay, now right now I'm not going to have anything returned from this guy, and I'll let you tell me why after we write this. So start thinking in that direction. So context switch out, what are we going to do? Let's see. Okay, good. We're going to set this dot cur PCB dot, I don't think we have a way of setting the current program counter. So what we need to do is go into our PCB data structure. We have a private variable program counter. We've given ourselves the ability to get that program counter, but now we need to give ourselves the ability to set that program counter. So as we are transitioning a process out of the CPU, we can rewrite to that process. We're storing the current set of data from the processor. Here's what the next, this is what your current program counter is, and here's your registers. So we need to be able to write those things back to the PCB data structure. So the next time it comes through line, it's going to be able to tell those back to us. It's going to be able to remember them. So we're going to have a method, public void set program counter. And this guy will take in a long program counter as a parameter. And we'll set this dot program counter equal to program counter. All right, so we just added a little ability to our PCB. So now we can tell the PCB, by the way, here's your new program counter. Okay. Go back to the CPU. So now we can tell this PCB, set your program counter equal to this dot cur program counter. So as the PCB as a process is leaving the CPU, we need to store all the information related to that process back into the PCB so that we can reload it later. So during the context switch out, one of the things we're going to do is we're going to let the PCB know what the current program counter is, so next time it knows where to start. Okay. Then we need to go ahead and store the registers. So we have a collection of the current state of our registers right here. Now notice we haven't actually started writing decoding, and we haven't decoded instructions in our CPU yet. So we never actually change our registers at this point, but we will. Okay, so we can trust that program counter is going to change from what it originally started as, and the registers is going to change from what it originally started as. Right now, they're real values, they just haven't changed since the last time we looked at them. So now we need to store the current contents of the registers back into our PCB. Now our PCB currently has the ability to give us the registers. Okay, so we can say get the registers, it returns it as an integer array, and it just gives us that variable, the registers. So we already have access to our PCB's copy of the registers. So here's the question. I want to write the necessary code here to copy the contents of all the current registers, that is, the CPU's actual physical registers, into our PCB's registers. Now the limitation I'm going to put on this is we are not allowed to add any more code to the PCB for this particular solution. That is to say, you're not allowed to write set registers. It's not a trick question. It's a how well do you understand pointers question. If I say, context switch out, if I say, is it an integer array? Yeah. Int array temp, well here, let's call this PCB registers, is equal to this dot cur PCB dot get the registers. What is PCB registers? After this line of code, what will this guy hold? Pointer to that array. Is it a copy of the array or is it the same array? Same array. So cur PCB dot get the registers is just going to hand us a piece of paper with the memory location of where the actual array is in memory. I have direct access to it now. I don't have to now go back and set it over here. I could just change it up here. Make sense? If I hand you the address to my house, you can go to my house and spray paint my garage, and next time I come home, I'm going to see a spray painted garage. Right? Is that an invitation? Depends what you spray paint on it. Because I think I'd like a gigantic Awesome Fat logo on my garage. I think that would be really cool. But like actually look good, not what I've done in my inside the garage for the hot tub. Which is when it started going south with that spray paint job, then we decided to go more for the ghetto look. So we actually called it by its artistic name, and that makes it like, oh, we were going for that.
So what you're saying is you want a really, really nice picture on the outside, so then when you open it up, you're just disappointed.
No, I really want a really nice picture on the outside, and then somebody to come in and fix the inside. Who knows what they're doing with paint? That's the ideal situation. So just saying, if any of you are looking for extra credit and know how to paint. All right, so this PCB registers gives us a pointer up into real memory. Real memory. So we can go through and say, for int I is equal to 0, I is less than this dot, the registers dot length, which we know is the exact same length as PCB registers, right? We wrote our PCB registers, our PCB, in terms of our knowledge of what kind of CPU it's going to run on. Make sense? Okay? You know, we could have probably made, I think I probably mentioned this when we wrote it, we could have made an argument here to maybe put this into some sort of global data structure for us to ask, you know, architecture fake CPU 1, version 1, has 4 registers so that we knew what to fill it up with, but we just kind of hard-coded it in there. Not a big deal for what we're accomplishing here. So we know that the length of the registers is going to be the exact same length as the PCB registers. We don't need to check that. And then I++. And all we're going to do is we're going to set PCB registers at bucket I equal to this dot the registers at bucket I. And you don't actually need the this dot here. I just like putting it so I have less spelling errors because we've had some issues recently. You don't usually wear glasses, do you? Too tired for the too much staring at the screen. Contacts aren't going in.
Well, I don't actually have they're only for using the computer, but like if I use it without them for a while, my eyes just get like really red, and they're already.
I got you. So over the amount of World of Warcraft you've played in the last several days has actually temporarily damaged your eyes.
Yes.
Okay. Got it. Just want to make sure we have that literally on the record.
Enough for me to slow down and let you catch up.
I know. So upset. It's actually really disappointed to myself because historically, I've always been like so addicted to games like that, where I will just force myself to stay up until I would have just sat down and played until I hit level 100 and not stopped playing. I'm too old now. I can't do it. I had time. I could have stayed up for 7 or 8 hours last night to keep playing. I had like chills. My ears were ringing because I hadn't slept since the previous day at 2 a.m. It will happen to you guys. When I was your age, I could pull all-nighters easily. It's bad. You just think you're never going to get old. It goes way downhill. Between 33 and 36, I feel like I aged 150 years. This is an empty husk. All right. So, all right. So we have a pointer up to our registers, up in memory. We're going to overwrite the contents of that array with the same contents of our this dot registers array. Now, the question is, when I overwrite this is a programming question for you guys. When I overwrite the PCB register at bucket I with the PCB register at bucket I in the registers, if I were to later change this value, would this value also change? Why? What kind of values does the registers hold? Hold ints. What if they held pointers? Would it change? If I have two separate variables here, okay, each of you holds a piece of paper with my address in it, my address on it, okay, and I go up to Amish and I scribble out that address and write something else. Did that have an impact on this one? No. They both point to the same place in memory initially, but they're not linked to each other. That make sense? Okay, so we don't have to worry about any sort of weird linking issues here where the next value that comes in and we do our context switch in and overwrite what's in the actual physical registers. We don't have to worry about that having any sort of permanent effect on this particular PCB's registers. All right, so all we did here is we got a piece of paper that gave us the address of where that PCB's registers data structure is so that we can go and copy all the values into it. And that's what we did right here, copying them all over. Same thing as what we did for our context switch in. So we copied them all over, and now we're done. So every single time a new PCB comes onto the system, we must first context switch the current PCB out. Then we can context switch the new PCB in. So there's two context switches that occur. Make sense? Okay. So we're supporting that now. Let's look at how start works. So start for PCB is going to say, well, if there's currently not a PCB on the CPU, we don't have to do any context switching crap, right? But if there is a PCB currently on the CPU, we need to context switch the current PCB out. So that's this dot context switch out. Then we need to context the new guy in. This dot context switch in. Notice that this guy takes in a PCB. That is the PCB we're starting. Make sense? So this method, start PCB, is going to be called by somebody, probably our process scheduler. They're going to go to the CPU and say, hey, I need you to start a new PCB. Okay, CPU is just a machine. So the CPU is going to get interrupted to start the PCB. If there's nothing, if the machine's not currently doing anything, it'll just start it. Otherwise, it'll save the state of the current PCB it's working on and then load the new PCB on. After this if-else structure here, we know the CPU is ready to work, right? We know it's ready to work. What does it mean for the CPU to work? What does the CPU do as it relates to our processes, to our PCBs? Well, it processes. Okay, what do you mean by processes the code? You're right. Did you know you were right? Did you? So why did it take you so long to answer? Or is this just students being students at 10:30 in the morning? What does it mean to process the code? What does the CPU actually do to process the code? So at this point, we haven't written what the CPU does in terms of its actual work. We've written the parts of how does the process get to the CPU? How does the process leave the CPU? Well, what is it doing when it's on the CPU? Actually, the CPU's chugging away. What's it doing? You say process code. What does that mean? Answer it. Answer. Say it. Say it. Have you seen Back to School? Sam Kinison? He's dead, isn't he?
Yeah.
It's a funny scene in that. Not classroom appropriate, but it's a couple of choice words he uses, but it is funny.
That's what it says to do.
Okay. Well, what says to do?
The code.
All right. Who has the code? Who currently has the code?
CPU because it's loaded in.
Does it? Have we written that? CPU knows about the next line of code it's supposed to execute in terms of the number, the line number. So it knows, well, the next dude I'm supposed to work on, the next line of code I'm supposed to work on is line 17, for example. Well, where's line 17 actually stored? In the PCB. Our PCB has a collection of strings. That's our code. Those are our lines of code, right? So the PCB knows about line 17. PCB did have an initial program counter, but that program counter was the next starting point for it. So the only program counter we can trust after a PCB has context switched into the CPU is the CPU's current count. The CPU knows how many instructions it's processed. All right, so let's just use in our example here, current program counter after we context switched in got set to the starting point of our, wherever the PCB told you the starting point is. Let's just say it's line 17 right now, okay? So the guy's been through the cycle a couple times, whatever. We're on line 17 for whatever reason. So our CPU says, I need line 17. He's going to go to the PCB to get line 17, right? So PCB is going to give them line 17. It'll be actually line 18. The code at bucket 17, right? So PCB has an array of the code. It will ask for, so we can now come back to the PCB and say, what is line 17? Line 17 will come out as a string. CPU now has that string. We haven't written it yet, but just kind of speaking about this at the high level, CPU now has that string. What's it going to do with it? You said it's going to process it. What does it mean to process a string? If you remember back in our PCBs, we have a very simplified language that our processor knows how to do. This is Intel's latest, greatest. What do we know how to do? We know how to do just I/O. No instructions, no classification, not even going to prompt them for anything. Just go wait for I/O. We know how to do that. We know that. And then we have the ability to move things, either to put a literal value into a register or copy the value from another register into a register. That's the entirety of what the CPU knows how to do. We can't even do math. We can move crap around and go wait for I/O. That's it. All right? So very limited CPU. So what this stuff is that when I reference back to it, when I say other things, remember when I talk about CPUs and their magic tricks? CPU has a whole collection of magic tricks it knows how to do. That ultimately, if a programmer writes their high-level code, it gets compiled into low-level code, those magic tricks get called in a certain order, and actual programs run. Okay? We're going to have very limited programs on our... they're not going to do anything. They're going to wait for I/O. They can't read it in, but they're going to wait. Okay, so we're going to simulate them waiting, and then we're just going to move values around. We can't display them. Can't do anything with them. We just move them. That's it. Okay, so our CPU that we're writing in here, our virtual CPU, which is obviously going to go mainstream, has a very limited set of magic tricks that it knows how to do. 3 different things. Okay, so to process an instruction, we need to look at the string that we were given when we request the next line of code from our PCB. We to look at that the next instruction, and that instruction needs to be essentially parsed, right? It's either going to say IO, which means that we immediately interrupt the CPU and context switch this guy out, go to our process scheduler and say, I need another PCB. Current dude isn't ready to continue. Make sense? Current program's working on the CPU, hits an IO request. I'm done working on them because the CPU's job is to stay busy 100% of the time, or as close to 100% of the time as possible. Never hits that, but, well, never is a strong word. Rarely hits that. Most of the time it's idle 98% of the time, so it's not busy at all. But in any case, as soon as the CPU hits an instruction that is IO, it's going to immediately get interrupted. So immediately say, I can't continue with this PCB. Context switch it out. Let the process scheduler know I need a new guy. Process scheduler will then say, you next in line, context switch in. Keep cooking. Now, if the instruction's not IO, CPU is going to get the instruction. It's going to say, oh, you're not an IO instruction, so I don't need to interrupt right now. Don't need to context switch out, then context switch in. So instead, I'm going to parse this instruction. Good news is we know it's a move instruction. If it's not an IO, it's a move. The only question is what are we moving? So we're going to parse this on one of our instructions is move some number into, then followed by a comma, lit. This is just a string, the string lit that lets us know the next guy is a literal. Some number. Okay? So what we can do is we can go ahead and split this on a comma. We know it's going to be a move, so in our current parser, we don't have to check for the move we don't want, other than the fact that we need that the destination. Which really, shouldn't these be colons? So we can parse that value out. If we're splitting this on the comma, the left half should be move colon the register, the destination. The right half should be lit colon the value, or register or reg colon the position. Why didn't somebody tell me to put the colons in here when I wrote this? I was testing you, obviously. We're going to let State Farm off because he can't see. Eyes are all puffy. So, aren't they? They kind of are.
Yeah.
It's not healthy. I think you should take at least 5 days off. Maybe 7. Give me some wiggle. So anyway, I need a buffer. I might only be able to play about 6 hours a day before I'm gone. All right, so we need to get the next instruction. So we're going to create a little method in here for our CPU. And the nature of this method is actually going to change, but for right now, we're going to just write a method called process. That's what the CPU does. It processes. So we'll have private void process. Okay, so what does it mean to process? First thing is we need to request the next instruction. That is the instruction at cur program counter. We're only processing after something's already been context switched in, right? So we're going to say PCB, we need to get the instruction at position program counter. Does PCB currently have a way for us to do that? I don't think so. So we're going to have a public string get instruction and it'll take in a pos position. And we're going to return, for right now, let's just assume that the instruction, that we're going to be checking that something is, so we haven't run out at the end of a program. We're going to check that someplace else. So we're not going to make sure that pos is a legal position in that array. We'll just assume it is for right now. So this guy's going to return this dot the code at bucket pos. Now, remember, our program counter is a long. Program counter is a long. So the number of instructions that we're going to support in our example here is a long. But because we're implementing this in an array, and arrays are going to immediately give us the limitation of dealing with only ints. Arrays are indexed via int. So the biggest array that we can create is an array with 2 billion buckets in it. Because it is using int. It's possible behind the scenes it uses an unsigned int. If that's the case, it will let us have 4 billion buckets. But definitely not bigger than that. So it's an int that we use to index an array. What if we needed to store more than 4 billion things? Go to a linked list or another structure, some sort of other structure, right? Not going to deal with it. We're going to use that as some more trivia knowledge for us right now. So we're going to say get the code at the int version of pause and just hope for the best. Please don't pass me a program counter of type long that's bigger than 4 billion. KK, thanks. All right, so we'll get the code at this position, return it as a string. Okay, so now we've built into PCB the ability to request from the PCB a certain instruction. Go back to our CPU. So we're going to say this dot cur instruction is equal to this dot cur PCB dot get instruction at position this dot cur program counter. So we just retrieved an instruction from the PCB. Then we'll say this dot cur program counter plus plus. We just retrieved the instruction we're going to execute. Now we're going to move past that instruction so that the next time through here, we grab the next line of code. Now we're going to parse the instruction. Instruction. All right. So first thing we can check is see if the instruction is equal to IO. So inside here, we're going to have an implementation of which instruction this is. In actuality, on a CPU, the PCB is probably going to map those instructions into the numeric code for the magic trick the CPU is supposed to do. So we're kind of faking this at least a little bit, but at least we'll have pretty close to the right kind of flow through for how this all works. So we're going to parse the instruction. The first thing we might ask is if this dot cur instruction dot equals IO. If it's an IO instruction, what do we do? Context switch out. CPU can't do anything for this guy. He needs to go wait for IO. So we're going to say context switch out and get in the IO queue. Then context switch the next PCB in. Whatever that means. So we're just writing it in comments right now. We'll actually implement it shortly. Okay, so this is what we do if it's IO. Otherwise, it's not IO, must be a move command. That's the only other thing we support. Okay, so must be a move command. So we're going to go ahead and we're going to create a string array called the parts. And this guy is going to be equal to this dot cur instruction dot split on a comma. Okay, and what that's going to give us is it's going to give us an array where bucket 0 of the array is equal to something like move let's say that. Huh? Oh, thank you. See, I was testing you.
Pretty sure it's also supposed to be a space.
I don't think there is. Don't think there is. Ah! But I didn't for lit. This was my own error, so it doesn't count. I'm right. See that?
You just forgot the colon and you blamed us.
I did. When I'm wrong, it's your fault. The rest of the time, I'm right. This is the way this works.
Except you were wrong that time with the space, and that wasn't our fault.
What do you mean? I'm not wrong. Just look at it. There's no space there. I went back in time. I changed it at the point of creation such that right now my code as I've written is accurate. I'm only writing a comment too, so it's not even an error until you've compiled. All right, so in any case, bucket 0 might look like this, and bucket 1 might look like either lit colon 5, or it might look like reg colon 1. Oh, sorry. Reg colon 1, something like that. Those are our options for the right-hand side, bucket 0. Or I'm sorry, bucket 1. So the parts, I'm going to split our instruction on the comma. Reason for that is when I built our instructions here, we put a comma in the middle between the left and the right. So this will get me the left and the right-hand side. Make sense? All right, this is just programming fluff because we're parsing instructions that we made up. CPUs wouldn't actually do it like this. They do something else, but we're not doing that. We're simulating. All right, so these are our options that we're dealing with. So on the left-hand side, we know exactly what the destination is going to be. That is the registers at this position. Make sense? So we're going to go ahead and we're going to say how do I do this? I've become lost. Okay, here we go. All right, so we're going to have another string array called the right parts, which you know what I'm saying, Abe. And the right parts is going to be equal to the parts at bucket 1, which is the right-hand side, dot split on a colon. So that's going to give us a bucket 0 that either looks like lit or reg, and a bucket 1 that looks like a number, either a literal or the register index. So it could look like 2, it could look like 22, which would not be a legal register index. So we hope in that case this guy said lit. Okay, but it'll look like a number. Make sense what these two different splits are doing? This guy's splitting our instruction between its left and right half. This guy's splitting just the right half on its two individual values. What kind of value is it, and what's the value? So now we can ask the question, if the right parts at bucket 1, I'm sorry, at bucket 0, dot equals lit, that means bucket 1 will have a literal in it. Okay? And what do we put in literals? We put whatever that value is as an int. We'll store it at the particular register bucket. So the left-hand side will tell us what index we're going to. The right-hand side will tell us the value we're going to put there. So what we'll say here is we know it's a lit. We're going to store the literal in the appropriate bucket. Well, let's just say in the appropriate register. What's the appropriate register? It's the right-hand portion of the left-hand parts. So if we really want to be good programmers about it, we could maybe just create a second variable called the left parts. And this is parts at bucket 0 split on the colon. Right-hand parts will be bucket 1 split on the colon. But we already know that left-hand parts at bucket 0 will definitely say reg, because that's the only thing we supported, right? If we look at our PCB, I'm sorry, not reg, move. It'll always say move. That's the only instruction we support. So we're just going to ignore left at bucket 0. We know what it says. We are interested in, though, in the index. Which register is the destination here? So we're going to store, well, let's be explicit about it. We can actually do this before our if statement. So we're going to set int destination is equal to the left parts at bucket 1, which is going to be a string. So we'll say integer dot parse int of that string. So this will get us the index. We can even call it destination index. That gives us the index in our register array where we're putting our value, which is either a literal or another register. In this case, we're writing the literal. So we're going to say this dot the registers at bucket destination index is equal to integer dot parse int of the right parts at bucket 1. We know that's a literal. We know it's a literal because bucket 0 of the right part said lit. So this is going to put in the appropriate register of the CPU the integer version of the value stored in bucket 1 of the right parts. So it would say lit colon 5, for instance. This will store the 5 in bucket, whichever register we had selected. Else, store the contents of the source register into the destination register. So we'll say this dot the registers at destination index is equal to integer, we don't even need to say integer dot percent there, is equal to this dot the registers at bucket integer dot parse int. What int? The right parts at bucket 1. So we're going to overwrite our destination register with the value that lives in our source register, because the right parts at bucket 1 actually represents an index in a register. That makes sense? Okay, so at this point, we're processing an instruction. So what we need to do at the beginning of next time, I'll just write a little comment here. make the CPU process multiple instructions. So we just worked through one instruction and moved the crap around what we're supposed to do, right? We didn't actually write our context switch out yet because that doesn't make sense right this moment, but that's what we need to do next. Questions about any of that? All right, have a good weekend. And State Farm, get some sleep.
I
You rest.
like 9.5 hours.
Did you?